Logistic growth. We have seen that equations of the form dA dt is equal to Ka, where K is a positive constant, lead to exponential growth. It is unreasonable, in many circumstances, to expect exponential growth to continue indefinitely. Consider a situation like a bacterial culture growing in a dish, an experiment you may well have done in science. This is curve A and this is curve B. At first, we might expect exponential growth as shown by curve A. However, this cannot be expected to occur forever. The dish is only so big and the nutrients are limited. Curve B might be a more appropriate model, and we can see both of them have exponential or close to exponential growth at the beginning, but then as the bacterial culture gets large compared to the dish and the nutrients start to run out, we're going to expect to see reduced growth. Exponential growth is not a very sustainable state of affairs, since it depends on infinite amounts of resources, which tend not to exist in the real world. Exponential growth may happen for a while, as we saw with the curve above, if there are few individuals and many resources. But when the number of individuals gets large enough, resources start to get used up, slowing the growth rate. Eventually, the growth rate will plateau or level off, making an S-shaped curve. The population size at which it levels off, which represents the maximum population size a particular environment can support, is called the carrying capacity. It's an important term that you need to remember. This curve is symmetrical and has an oblique point of inflection when y is equal to half the carrying capacity. This is an important point that's used in many questions. So about there is an oblique point of inflection, and that is when y is a half of the carrying capacity, which, as we'll see below, is usually called K. Logistic growth is governed by the differential equation as stated on the formula sheet, and this is important because you want to use this as it is on the formula sheet. dp dt is equal to rpk minus p. And that gives us the solution p at any time t is equal to k p naught. P naught is the initial population, over p naught plus k minus p naught e to the negative rk t. Now I'm just going to point out something important here. We have dp dt is r p k minus p, and that means that dp dt is equal to 0 when p is equal to 0 or p is equal to k. And you can see that we have 0 gradient down here and a 0 gradient as we approach the asymptote. So when p is 0, when the population size is 0, there's no growth. And when p is at the carrying capacity, we get no growth, and that's why we get the asymptote there. I'm going to look at this in the next video. It's unlikely, especially in an exam, that you're going to be expected to actually solve the differential equation to go from here to here. Could happen in one of your school tests, and I'm going to look at that in general. We can show this by the method of separation and integration, as I just said. We'll look at that in the next lesson, where p is the population at any time t, p naught is the initial population, we're just using the regular notation that you're used to, k is the carrying capacity, as we mentioned before, r is the intrinsic growth rate. That's the rate at which the population would grow if resources were plentiful. So that's going all the way back to our initial situation, or our previous situation, where we have the exponential growth. In other words, it's going to be the growth rate for one of these situations where we get the exponential growth. This is a bit interesting. This is to do with COVID data, and we can see that this goes back to 2020, April 2020. And we've got a logistic curve mapped against an actual histogram of the cases. And you can see that we are getting this growth here, which looks a bit like this curve here. True data is never going to really exactly match the model. And you can adjust the model so that it matches better as well. I mean, that's one of the things scientists do. Now, it didn't actually go and do this bit because of measures like social distancing, washing hands, wearing masks and all that sort of stuff that was supposed to flatten the curve, and you can see that it did exactly that. The above graph was released on the 16th of April 2020 by the Australian Government Department of Health. Note that the cumulative cases demonstrate logarithmic growth, or exponential growth if you like. At this point in time, the government had implemented strict social distancing measures to flatten the curve, as I just mentioned, in order to keep the cumulative cases below the carrying capacity of the country's health services. And so this stuff is all practical and used in the real world.